Don't be worried, yeah, you will only stay during the presentation.
So thank you, Daniel, for giving me the opportunity to talk to the GLOBE program. So this talk will be about aerosols and their impact on air quality and climate. So I'm working at, just a word about my laboratory. I'm working at the Laboratoire d'Aérologie. As said, Daniel, it's very close to this site here, but we have also a very fancy site like the Pic du Midi. And we do research on atmospheric dynamics, meteorology and storms and extreme events. And we are also interested in coastal oceanography. And we have a department on atmospheric chemistry, where we measure the trace gases and aerosols, and we study the emission, transport, the reaction in the atmosphere, the deposition of the trace gases and aerosols, and also the impact on the climate and health. The topic is atmospheric aerosols, which means that it's fine particles that are in suspension in the atmosphere. It means that they are fine enough to be to stay in the atmosphere, not sedimented. So it's particles between tens of nanometers and tens of microns. If too large, like a fine beach sand, they will sediment. Usually we use the size of the particle to make category of aerosols, like the PM10, you must know, particulate matter below 10 microns in diameter, where you have crustal elements like dust, and the finest one, PM2.5, which means that the particles that have a diameter less, aerodynamic diameter less than 2.5. So the atmospheric aerosol is a quite visible phenomenon because everybody can see the pollution in the big cities and the reduction in visibility due to the particulate matter. And it's quite a huge problem for health, of course, for air quality, and also for climate. And I will talk more about that. So first, where are originating the particles? So there is two kinds of emission. The primary emission, which means that the particles are directly emitted as particles in the air. And there is secondary emission, which means that you have emission of precursors, like gases, will be oxidized in the atmosphere and react, and then condense into the particulate phase. Usually, this kind of aerosols, this kind of particles, are very thin in size. Oops. So the origin and the sources of the aerosols in the atmosphere are very diverse, which means there is a large diversity in the chemical composition of the aerosols. You have I will go into the detail, but emission from the desert, the fires, and the emission, of course, from the anthropogenic emission, I mean, the human-made particulate matter. So first, let's start with the desert dust. Desert dust is a major component of the atmospheric aerosols because very huge emission of dust are emitted from the desert due to the effect of wind on the arid and desertic areas. So the wind will uptake massive dust, like we can see this in the village in Africa. And the dust will be advected toward many places in the world, like crossing the Atlantic Ocean up to the US and the Caribbean. So this kind of aerosol is usually coarse in size because this is due to the impact of the wind on the surface, and it uptakes large particles. And it has a large impact on the aerosol optical dust and the climate. This is a microscopic pictures of the dust. You can see there is a large, different size and large diversity of the dust, like this large ovoid African dust made of quartz, big particle of 10 micrometer. But you have also very fine dust like this clay, and a very different kind of shape. So it depends on where the dust is originating from. If it's in the Sahel, the Sahara, or Middle East, so you will have different kind of mineral composition and different shape of the particles. Second one of large emission is the volcanoes. So the volcanoes emit both primary and secondary components. Primary is like ash, Here you have a big ash of about 30 microns in diameter. This is a big problem for visibility for the aircraft. So you know this volcano is in Iceland, which emits a large amount of particles, and so the air traffic was very disturbed during the mountains. It also emits gases like SO2 and H2S, which will condense in the atmosphere and make small particles, small droplets. And one of the large impact of this kind of emission is that these gases can go very up in the atmosphere, like in the stratosphere, and they stay for a long time, for months, and make particles in the upper troposphere and interact with the ozone layer and so on. The third one, major emission, is the biogenic sources. So for the biogenic sources, you have also two kinds of sources. The primary emission, like pollens, virus, bacteria, and debris of vegetation. Usually the pollens are quite large, but they can be transported very far distance. And you have also a lot of organic, volatile organic compound emitted by the vegetation due to the respiration of the vegetation, like isoprene, terpene. And this emission will be oxidized in the atmosphere and form new particles. And there is a lot of interaction between this kind of emission and the urban emission, for instance. They will interact. So there is a question about how the vegetation downtown the cities will interact with the air quality in the cities. One of the large emissions in terms of mass is the marine aerosols. So due to the action of the wind on the sea surface, you have emission of sea salt, like this particle here, which is like a square shape of about 1.5 microns. It's the second one dominant in mass after the dust particles, like natural aerosols. The surface, marine surface, emit a lot of sulfur DMS, dimethyl sulfide gases, will we make also very thin particles and volatile organic compounds. So the sea surface is a huge source of natural aerosols, both from primary and secondary aerosols. And one type of emission which is directly linked to the human activity is the combustion emission. So because of our activity, we emit a lot of gases and particles in the atmosphere, and especially particles due to the use of fossil fuel and biomass burning. And I will go more in detail about this kind of emission. For instance, looking at if you collect this kind of particles on a filter, you can see that the filter will change, the color of the filter will change according to the type of emission, from very dark for diesel emission to quite orange for biomass burning with a smoldering emission, which means that in this case you have a lot of soot, while in this case you have soot and a lot of organic material like the orange smoke, which will then make secondary aerosols. So there are some diversity in the emission of combustion aerosols. Looking at the structure of this kind of aerosols, they are very complex. So you have this image of soot. Usually the size of the spherules here are about tenths or less nanometers. They make like a chain. And then when they age in the atmosphere, they are emit as soot. And when they age in the atmosphere, they form like more spherical particles embedded with organic matter inside. So this kind of aerosol is quite complex to study because of this structure or its chemical properties and its aging in the atmosphere. So we'll talk about later about the black carbon, which is one of the characteristic of the combustion aerosol emission. I want to show you one simulation of the global aerosol system, which is really interesting to see, made by NASA. Not this one. Okay, this is really beautiful. I like this picture, especially on this screen. It's amazing. So there is no legend on this picture, but it talks about the global emission and the transport of aerosols in the atmosphere. And you have a color code, which means that green is more combustion aerosols, white more urban anthropogenic emissions, pollution, we'll say, and the red is more dust. So we can see that the biomass burning in the tropics area where you have the forest is really the major source of combustion aerosols in the Brazil and so on, the burning of the forest, and in the Central Africa too. You have this huge emission of the dust over the Saharan and Sahel desert, which is transported by the westward winds up to the US and the Caribbean. And the pollution from the US, Europe, and especially from Southeast Asia and China, where you have huge amount of emission from coal burning and traffic also. And this aerosol here are the emission from the sea surface, the sea salt, because you have very high winds that uptake the sea salt on the surface in this area where you have the highest wind speed. What is interesting to see is, of course, the transportation of all these particles, which means that if you emit somewhere, then it will be transported almost everywhere. But the transportation really depends on the altitude where it's emitted. For example, the dust in the Sahara is really uptake at about 5-6 kilometers. That's why it's being transported either to the US or to Europe. Sometimes in Europe we see this dust on the snow during the winter. You have the yellow snow. That is due to the deposition of dust on the snow. Usually at the spring, late winter. Okay. So this is an idealized view. I mean, it's not reality, huh? Okay? Just a model. Okay, let's talk after this. Let's talk a little bit more about measuring the aerosols. So one of the primary parameters, this was in this simulation of aerosol, is its aerosol. It's a optical depth, which means how it can interact with the solar radiation. So to measure this parameter, is the physical principle is quite simple. Just to look how the particles scatter and absorb the solar radiation. So it's this aerosol optical depth is a dimensionless parameter because it's linked to the attenuation of the aerosol over the atmospheric column. And it's ranged between 0.01, let's say, for very clear sky, very blue and no pollution, nothing, to about 2 to 3, which means you are in the dust storm and you can't see the sun, barely. This parameter is wavelength dependent, which means that it depends on the wavelengths you are the observation you make. And this wavelength dependence is due to the size of the particles. The larger they are, the smaller the wavelength dependence is, which means for dust, for example, for large dust or large sea salt, you will have almost a white signal, like clouds, so white shape. While for fine particles, like pollution particles, you will have a strong wavelength dependence. And this is really important for the climate system. So this